Welcome to Mrs. Lee's Chemistry Academy, where no students are left behind. Today we're going to talk about gas laws on gas velocity and real gas behavior. This is tied to the learning objective from College Board 2.4 that the students able to use kinetic molecular theory and concepts of intermolecular force to make prediction about the properties of gases, including both ideal and non-ideal behaviors. That the student can qualitatively analyze data regarding real gas deviation from ideal gas behavior and relate them to molecular interactions. That the student is able to relate temperature to the motion of particles, either by particulate drawings or by representation of average kinetic energy and distribution of kinetic energy of the particle, such as the plot of Maxwel-Boltzmann Distribution curve. Now, in the kinetic molecular theory, it is postulated that average kinetic energy of gas particles is directly proportional to its temperature. As temperature in Kelvin increases, gas molecule moves much faster because they have greater kinetic energy. Now, the kinetic energy is dependent on mass and velocity of the molecules, where Ke is equal to 1/2 mv squared. So in a mixture of gases, lighter molecules travel faster than more massive ones that would be traveling slower at the same temperature. The average velocity of gas particle is defined as the root mean square velocity, and it is equal to the square root of 3RT over m. It is directly proportional to the square root of temperature, T in Kelvin, but inversely proportional to the square root of the molar mass, m, in units of meter per second. So R is 8.314 joule per K dot mole. M is the molar mass in kilograms, because 1 joule is equal to 1 kilogram times meter square per second square. Therefore, we must be very careful that the molar mass be calculated in kilogram. Let's calculate the root mean square velocity of nitrogen when we put in the molar mass of 0.028 kilogram per mole of nitrogen. We get 515 meters per second. Now let's calculate the root mean square velocity of hydrogen when we put in the 0.00202 kilogram per mole of hydrogen. We obtain 1,920 meters per second as the root mean square velocity of hydrogen. Now when we compare the two, we find that the hydrogen is moving at the rate of 3.7 times faster than the heavier nitrogen. Let's look at the Maxwel-Boltzmann distribution curve of molecular velocity by molar mass. Here we have oxygen, nitrogen, water, helium, and hydrogen for comparison. And we find that as we move toward the lighter molar mass molecule from oxygen to hydrogen, that the distribution is more spread out, and the average velocity is much higher for hydrogen, which is about 1750 meters per second, and for oxygen is about 400 meters per second. Another Maxwel-Boltzmann distribution of molecular velocity by temperature. This is one kind of ideal gas at various temperatures. As temperature goes up from 273 Kelvin all the way up to 2000 Kelvin, you find that the distribution curve is more spread out and the average velocity is increasing to about 1100 meters per second. Now let's bring our attention to Graham's law of effusion. In the diagram, you see two chambers. The left side contains the gas molecules, the right-hand side is a vacuum. And in between, on the divider, we have a little hole, a little pinhole for the gas molecules to travel from the left container to the vacuum one at a time. We call it effusion. And the relative rate of effusion of two gases through a pinhole into a vacuum are inversely proportional to the square root of their relative molar masses. Here's the formula. Rate of A over rate of B is equal to the square root of molar mass of B over molar mass of A. Now, in my experience with students is that they tend to put the number in the wrong place, so be very careful The lighter molecule A that travels faster is in the denominator on the right side of the equivalence relationship. Practice problem number 1. I have a long evacuated tube, and on two ends I use cotton swabs wet with ammonia and hydrogen chloride. Now, after a while, these two gases will travel randomly until they meet to form a white cloud called the ammonium chloride. Calculate the relative diffusion rates. Now here we use the word diffusion. Diffusion meaning gas molecule travel randomly, but diffusion meaning that they have to travel through the little pinhole. However, the same formula applies. So now we compare the rate of ammonia to the rate of hydrogen chloride, which is the square root of the inverse relationship of the molar masses. We obtain 1.5 approximately. That means ammonia is traveling at the rate of 1.5 times faster than hydrogen chloride. The white cloud is formed at about 1/3 of the length from the HCl end and 2/3 from the ammonia end. As you know, ammonia gas travels much faster than HCl, therefore it's expected that it would go further down in the tubing. Now, let's examine the difference between ideal gas and real gas behavior. At high temperature, gas molecules, they collide with greater kinetic energy and therefore will then minimize their intermolecular force of attraction. And also at low pressure, gas molecules are spread far apart, so they don't have a chance to really exhibit intermolecular force of attraction. And these are conditions that are great for ideal gas behavior, high temperature and low pressure. However, if we go to low temperature, then the gas molecules will slow down in their motion, and then they begin to exhibit intermolecular force of attraction. And at high pressure, gas molecules are drawn close together, and they have a chance to exhibit intermolecular force of attraction. And then they begin to behave non-ideally or deviate from ideal gas behavior. It is important that we note these conditions. As we know, the ideal gas law is PV is equal to nRT. Mr. Van der Waals, he proposed this equation to account for some of the deviation in their behavior. Now, the correction factor for the pressure is A times N over V squared. The P stands for the observed pressure, which is really less than what it is supposed to be had gas molecules behave totally ideally. Because now they don't behave as ideally, they have intermolecular force of attraction, and that would reduce the pressure somewhat. Therefore, the pressure observed is actually less than what it's supposed to be. Now, we also assume that gas molecules have no volume, but in fact they do. Therefore, the volume occupied by the gas molecule should be accounted for in the total volume of the container. N times B meaning the volume occupied by the gas molecule, which is moles times the constant B. So now we have the modified ideal gas law behavior equation as Van der Waals equation with the two correction factors built in. The next one deals with the real gas at high pressure. Now, if they behave ideally, PV is equal to nRT, therefore the ratio of PV over nRT should be equal to 1. Now, as you can see in this diagram, as pressure goes up, then there's a deviation from the PV over nRT equal to 1 relationship, and you can see these lines are beginning to skew upward, having a positive slope. That means at high pressure, they exhibit intermolecular force of attraction, they come close together, and they don't behave ideally anymore. The next diagram deals with real gas behavior at different temperatures. Now, when the temperature is high, sufficiently high, you can see that the PV over nRT conforms to the ratio of 1. But when temperature goes down to 200 Kelvin, now you can see that there's a greater deviation for non-ideal behavior, because at low temperature, gas molecules slow down in their motion, in their movement, and they begin to exhibit intermolecular force of attraction. Practice problem number 2. There are 4 identical balloons, each filled to the same volume at room temperature and 1 atmospheric pressure with hydrogen, nitrogen, carbon dioxide, and chlorine. And you may want to take out your pen right now and draw these 4 balloons and put in the gases in there. Rank the gases in order of increasing kinetic energy. Now, as we know that at the same temperature, gas molecules have the same kinetic energy. So they have the same kinetic energy, and there's no difference between them at all because they have the same temperature. Next question says, rank them in order of increasing number of molecules. Now going back to the ideal gas law, PV is equal to nRT. So if they have P, V, and T being the same, and R is the same, that means N, the moles of molecules are the same. That means they have the same number of molecules. Rank them in order of increasing average velocity. Now, as you know, velocity is inversely proportional to the molar mass squared by their square root. And here, chlorine is the heaviest one with 71 grams per mole, and carbon dioxide 44 grams per mole, nitrogen 28 grams per mole, and hydrogen 2 grams per mole. Hydrogen is the lightest, therefore it would be having the highest average velocity. Now, which balloon would contain the gas that would be expected to deviate most from ideal gas behavior? Now, looking at all these gases, they are all nonpolar gas molecules with LDF. Which has the greatest LDF? Chlorine. Why? Because it has the most number of electrons, and that would contribute to greater LDF, and therefore they will have a little bit more stickiness together than other gas molecules. Therefore, the one expected to deviate most from ideal gas behavior is chlorine. Which one will diffuse fastest out of the balloon? Again, this is hydrogen because it has highest root mean square velocity. So in summary, what have we learned today? One, we learned that the average kinetic energy of gas particles is directly proportional to temperature in Kelvin. 2, the particles have a range of velocity varying with their molar masses inversely but directly to the temperature. That gas effusion rate is inversely proportional to the square root of the molar masses, known as the Graham's law of effusion, and that gas behave ideally only at high temperature and low pressure. And if it is low temperature and high pressure, there's a lot of deviation. And lastly, Van der Waals equation, which modifies the ideal gas law equation to account for the volume occupied by the gas molecules and the intermolecular forces exhibited by gas molecules at high pressure. I hope that you have found the above lesson to be useful to you. I look forward to hearing from you any comments, and I do hope to see you again next time.